Sure. And this will work out, you think, if I stand here?
Yeah. You can move around as well if you want. Yeah, but yeah.
And the mic will still pick it up. It's this mic on my
It
laptop.
should be good enough.
Okay.
Like, at least from the English times that we are trying. So.
Okay.
Thanks, you know, your computer's mic.
Yeah.
Otherwise, it will be a forcing function for people to come in person.
Do you do something with the recordings?
So we have a YouTube channel.
Oh, you'll put it on there? Okay,
Post it
great.
on it.
Yeah.
If you're okay with that.
Yeah, we'll see how the talk goes. See how hard your questions are. Oh, but your questions won't get picked up, right?
But your
By the
answers
recording. I'll try to remember that. It's good teaching practices to repeat, right?
You had other people introduce you yet with that talk title, and has it caused problems in the past?
It's a brand new talk title. But our paper has that word in it. And I have been entertained by how people pronounce it, although I have to say that Isabel Papadimitriou had some notes for me about how I pronounce it. And she's Greek, so I trust her. I'll do my best. I still have some anxiety about this one. That's why I was asking, if you have been tasked with reading my title to introduce me, maybe you want some tips.
I was gonna say Archai.
That's what I say too, yeah.
Okay.
And this one?
Palimpsestic.
Perfect, all right.
You say it differently?
I think that I tend to say that P, palimpsestic, but I don't think you shouldn't. I think it's like it's the Greek character psi, PSI, that one.
So the P is.
I think the P is basically silent. Don't quote me on that. I gotta ask Isabel.
Have that from the recording.
But okay, yeah, we can get started. So, hello, everybody. We're very fortunate to have Christopher Potts here with us today to give a talk at our seminar. He's a professor of linguistics at Stanford with the courtesy appointment in CS, and he's part of the famous Stanford NLP group, as well as Stanford AI Lab. His research uses computational methods to explore topics in context-dependent language use, systematicity and compositionality, model interpretability, information retrieval, foundation model programming, and he has papers on all sorts of other topics. And he's published papers across venues, across numerous disciplines. He won prestigious awards such as Best Paper and the Test of Time Award at ACL. So we're very lucky to have him today. And his talk today is called The Archai of Palimpsestic Memorization. And I'm excited to hear what the hell that means.
That's right. Thank you so much. It's really great to be here. And I think this will be a fun talk. I'll tell you a lot about palimpsests throughout the talk today. You'll get a feel for that. Archai is meant to invoke beginnings. It's the plural of the arche, which would be a muse of origins, maybe a lesser muse of origins. That's where that comes from. I have really tried to lean into the Greek influenced English words and also into a theme of adventure here, because this is really an intellectual adventure that I'm trying to reconstruct. This is a palimpsest. A palimpsest is any material that has been written on and erased many times, typically over the ages, with the effect that older texts are visible below the newer texts. And so these pieces of material become kind of records of all the writing that has happened to them. And the guiding metaphor / insight of the talk today is that language models are palimpsests with respect to their training examples. Each one gets kind of etched into it in a very deep way, with older examples from earlier phases of training fainter in this memory than later ones. And it's that insight that leads to the palimpsestic tests for model provenance. So keep that in mind, and we'll keep returning to that. The talk today is basically a reconstruction of the motivations and the thinking behind this paper that we did at NeurIPS last year called Black Box Model Provenance via Palimpsestic Membership Inference. I am pleased to say that currently, because the NeurIPS proceedings have not been published, there are no occurrences of the word palimpsestic throughout any of the NeurIPS proceedings. So we will be the first. And then I'm hoping, of course, we get many citations, so this number goes way up as people cite the paper. The focus of the paper is on tracking model provenance, which I take to be an important issue for the current moment of AI, as we have so many different models floating around in the ecosystem. And let me just offer you a few motivating stories for this. This is a case that happened a couple of years ago, a little bit embarrassing here. This is a team of undergrads at Stanford. And they had to apologize to this Chinese startup that's called Model Best because they had stolen that startup's model and were purporting to have created their own model. And the way they were caught is by a bunch of really clever sleuthing around the nature of the model weights. And indeed, in one interesting twist, the team itself had been interested in these ancient Chinese texts. And so they happened to have trained their model to be good at those texts. It was a very idiosyncratic thing to do, and those things became kind of canary strings for them to detect that the Stanford team was using that exact same model. This is another case from Reflection AI. They claim to have achieved a real breakthrough in language modeling, and people pretty quickly discovered that the breakthrough was just an anthropic model. And again, they did that through lots of clever looking at how the tokenization was happening, in addition to getting the model to kind of go off script from its system prompt and reveal who it was. But all of these things have required really expert, bespoke investigation to figure out the true origins. And I think these questions are becoming more pressing. It's wonderful that we have so many open weights models out there in the ecosystem now, but that does have the effect that some of those models are going to be used for surprising and maybe really problematic purposes. And it might be crucial for us to be able to track back to the original model for various reasons. And one example of that, this comes from Stephen Casper. He's just been tracking the number of models on Hugging Face that are literally being advertised as having their safeguards removed. And I think it's going to be an important part of piecing together the consequences of this, that we can figure out exactly which model has been manipulated in that particular way. So that's meant to motivate model provenance. Now, right at the start here, what I want to do is just give you a sense for our palimpsestic tests for model provenance. And my hope for this current moment here in the talk is that you understand what I say, but have no idea why I'm saying it. Because that was the position that I was in. I understand the nuts and bolts of what you're describing, but I am not sure why you came up with this or why you think it would be useful for tracking model provenance. And then this talk is going to be about filling in all those gaps so that if I've done my job, by the end of the talk today, you should feel like, of course, we should be constructing tests like this. So here's how the test works. Let's imagine that we have a model, call it M1, that we have created, and we're very proud of it. And maybe we put it out into the world for people to use. There is another model, M2, that's maybe embedded inside a larger language model service of some kind. And we form the suspicion that despite what the M2 creators are saying, that's actually just our model, or maybe a derivative product of our model after some fine tuning or something like that. And we want to test that claim. Here's how we'll do this with these palimpsestic tests. The one thing we need to have done is keep track of our training data order. That's a sequence of examples, a sequence of texts, and we just array those out in the order that we use to train the model. So here I've just got 3 of those texts. For the tests, all we're going to do is take that model M2 and run it on exactly that sequence of examples and record the log probabilities that this model M2 assigns to each one of those texts. So we get a little graph like this, and then we can just study the correlation. And if there is a strong correlation between the training order here and the log probs assigned by M2 to that text in that order, then we will have strong evidence that in fact M2 is an identical copy of our model or a derivative thereof. That's how the test works. And just very quickly here, the question we're asking is, can we reject the null hypothesis that the training order down there and the log probs assigned by M2 are independent? So that is how the test works. And if you're like me, when this was presented to you, you think, that seems like a very surprising claim to be making. Why would the training data order carry that much information that we could use it for testing in this way? I'm happy for questions. Did you have a question?
Yeah, I was just curious about how you define training it up, training order in the sense that same data point might appear multiple times. Training, what kind of rank would you give that data point?
It would just be, so your question is if we had repeated examples from the training data order, we would just include that as part of the training data. You can imagine that you've just got your big sample of text you're going to train on. And presumably when we created N1, we did some shuffle of that. That ordering is the order that we're talking about.
Just a follow-up there is just like if that same data point I'm using for instance with M2, I just get a single log from you, right? So where do I plot it on the curve that we are trying to put in?
I mean, and we would just treat them as different points in this order, and we would just get the log props, and they would be identical in that case.
Oh.
But that's just yeah, that sounds fine to me.
I'm just curious, so the log prop of the N1 doesn't matter here? Because when you mentioned some articles may be more easier to fit than the other.
It's just not used for the test. Is that your question? I'm not
Yeah.
sure whether it matters or not. I mean, it certainly does matter in some sense, but
I mean,
test,
it doesn't use that.
it doesn't use it yet.
I may miss that the 1, 2, 3 is the actual training data of M1.
Yes,
So
that is
you
the crucial
assume you
piece.
have the access.
We need to have kept track of exactly that piece of information.
Okay.
And in fact, here's some properties of the text, just to kind of get you on board here. For properties, it has high power. I'll try to show you that later. It's transparent. We don't need to keep any facts about M1 private. We can, in fact, release the training data order. We do just need to have kept track of it. That is the one requirement. It's also non-invasive. We don't need to mess with M1 in any way by planting sentinel strings or anything like that. And we don't need to mess with the training data or mess with the model weights or any of those things that you might do to kind of fingerprint your model. And in terms of the virtues, this will give you a sense, I think, for how the test actually works. We can do it on subsets of the training data order, so you don't need to have your whole trillions of tokens there. You can do it on a few million contiguous subset of the training examples. It works even if M2 has been fine-tuned or souped or continue pre-trained, all those things that people would do to create a derivative product, the test is robust to those. It works even without exact log probs. So if you're in a position where that service behind M2 doesn't let you have the log probs, you can estimate them by sampling from the model, and those estimates will be good enough to support running the test. And I'll show you this later. A variant of this works even with just texts that are sampled from M2. So no direct access to the model. You can imagine that in that scenario, M2 is spraying examples out onto a social network, maybe spreading disinformation, and we want to know whether it's our model that's behind all that disinformation. That's a context in which we could gather all those texts and then use them to run a variant of the test that I'll show you later. All right, so if you're like me, this is where you're at. We can correlate the training data order with the log props. That made sense. But why on earth does that work? And maybe more interestingly, how on earth did the authors come up with the idea to try this at all? And I don't mean to sound ironical about this. So I am a member of the author team here. I'm one of the senior authors. But I just want to be upfront with you that Rohit, Jing, and Sally came to me and to us with this idea basically already proven out. I'm going to call this entity RJS. So RJS came and they showed us some plots that I'm going to show you later. And they said, hey, look, we think this will support model provenance testing. And my reaction was bewilderment. And so what I wanted to do for today is essentially make myself less bewildered and with luck, make you less bewildered. So I have structured this as a journey here. We're going to travel to the palimpsestic test, and we're going to do that through a bunch of the literature, because what I'm going to try to show you is that RJS were reading very deeply in the literature on memorization. And as a result of that, the test became apparent. I still think they needed some kind of cosmic inspiration to actually formulate this as a test. That still surprises me, but my students continually surprise me in that way. So in a way that surprise is not surprising. But I think I can get us right up to here, and then maybe you'll all have the flash of insight as well. So here we are at UCLA campus. This is Royce Hall, and I have chosen this because this is the building most likely to play Stanford University in the movies. So I have a special fondness for it. And as I said, if they make a movie about me, my office should be right here. And we're going to travel through a bunch of these papers that came before ours. And at the end of that, we'll have reached the tests. That's the idea. So here's the overview in a bit more detail. I want to show you something about the relationship between memorization results and log probabilities. Then we'll talk about how there are many kinds of memorization, and both these things are going to feed into taking an expansive view on what counts as memorization for language models. Then we'll look at memorization profiles. Those first two sections will set us up to understand all of that evidence. And once you've seen the memorization profiles, the palimpsest itself that I referred to is very easy to see. And once you've seen that, you can formulate the tests. And then I'm hoping we have time to just think expansively about where we might go next with tests like this to increase their power and just think creatively about what's possible in this space. I did write a blog post about this because I really wanted to systematize my thinking about this and assemble all of the evidence. So if you want to go through these results in a more leisurely way, there it is. It's also linked from my personal website. Shall we dive in? Here we go. Let's start with these two preliminary things. The first is the relationship between memorization and log probs. This is Carlini et al. 2019. This is a really important foundational paper in the study of language model memorization. And one of the many things they do in that paper is just point out that there is a correlation between memorized strings and log perplexity, which is going to be like just the average, negative average of the log probs. So you can think of this as the same kind of quantity we'll be tracking later. And they're just observing that the memorized strings have the lowest log perplexity. And in fact, this is nicely organized because near neighbors of the literal verbatim memorized string also have low log perplexity kind of traveling out to strings that are unrelated. For better or worse, after Carlini et al. 2019, most people moved to discrete measures of memorization for language models, just whether it produced exactly the right string. And that actually makes it hard to see the memorization profiles through all this evidence. Luckily, though, this paper here, Prashant et al. 2022, was very systematic. And so they offer a bunch of evidence showing that memorization and these notions related to log probs are highly correlated. So prompt PPL is the perplexity for the prompt string you use to start the memorization. Continuation PPL is the actual continuation of the verbatim memorized string, the full sequence, and then you see the loss. And systematically across these plots, you see that the memorized things have lower values, which would be higher log probs for all of these different measures. And that too is beginning to associate log probs with memorization. Now, there are a few generalizations you could reach at this point. We might want to think about this. First, memorization implies higher log probs. I think that's true in the sense that you just saw from those plots. In general, memorized strings will have higher log probs. The reverse will be much dodgier. I don't think we should just leap to the generalization that higher log probs implies memorization, unless you're on board with me in taking a really expansive view of what memorization is like. But I think really what we need to continue our journey to the tests is just that memorization is correlated with higher log probs. And if even that is making you nervous, what I really need you to do as a kind of leap of faith then is just accept that behind the evidence that I'll show you later, which will use discrete memorization measures, you would find higher log probs for the verbatim memorized strings. So here we are in our journey. Got a little bit of evidence and one heuristic. Memorization correlates with higher log probs. Second preliminary, there are many kinds of memorization. Now, I think that in general, when people talk about memorization for people and also for language models, they have in mind verbatim memorization, which is like you either know the first n digits of pi or you don't, right? You can either recite the lyrics to the song or you can't. You either perfectly are able to recount the poetry or you're not, right? As a kind of all or nothing thing. I think it's interesting that we think about that, but I think it's just a stream on a continuum, which could have lots of imperfect kind of memorizations along the route. Obviously, if you get one digit wrong or miss a few words in these texts, you still, in some sense, have done a substantial amount of memorization. And I would encourage you to think that way even if you're trying to connect memorization with things related to copyright and so forth, because I could just tell you that at least in the US, verbatim memorization is not the standard for whether something was stolen. And here are just a couple of court cases where in each instance, we're talking about texts that ran afoul of copyright law, but just included snippets and paraphrases and so forth of the original text. So even in the space of legal issues, we don't have verbatim memorization as our standard. So we should think about a full continuum. You might also think about an orthogonal dimension, which is rote memorization versus reconstruction. If you have memorized a bunch of digits of pi, you probably just had to rote memorize all of those digits, unless you constructed a very elaborate memory palace or something like that. But if you're asked to memorize, say, song lyrics in a language that you speak, you will have lots of things that you can do to avoid literally having to memorize each one of the words. You have lots of, in this case, structure around this repeated rhyming pattern. There's also lots of metrical structure that you can benefit from. And the fact that it's simply English, which I'm presuming is a language you speak, will also give you lots of parts of this text that are essentially determined by your knowledge of English. And so in effect, you might memorize just a few pieces of this text as kind of keywords, and then language modeling as usual might take over the process of recitation. And I think this is true for people, but for today, it's more important that this is definitely true for language models. And in the paper that we did, that Jing Wang led, my student, Wang et al. 2024, we talk about memorization illusions. This is one of the memorization illusions. This is for Pythia 6.9 billion deduped. We gave it this very long prompt full of obscure words, and it produced this output verbatim. Now that is a training example for Pythia, but from a much later checkpoint. At this point, this model had not seen that sequence. It's a memorization illusion because it's part of a template, a templatic kind of thing that is very frequent in the training data. And so the model just filled in the blanks in the most likely way. And those actually happen to correspond to a later training instance. And that shows that what looks for all the world like an instance of rote memorization might be a mixture of that plus language modeling as usual. Here's just a bit of evidence that it was not in the training data for that checkpoint. Final thing, semantic memorization could also be important. If you memorize a fact like Tokyo is the capital of Japan, that's not a string that you memorize, but of course it does relate to a bunch of other strings. And for language models, this relationship here is going to be especially tight because the only way they can acquire facts like this is through strings like this. And in turn, their knowledge in some deep sense of this fact is going to have an impact on the log probs they assign to all of these different strings. It might give them a feel of something like memorization. So we could think about all of this coming together as a perspective on metrics that we might have for memorization. Here I've got the start of a sentence from Harry Potter, and you could imagine that we have it complete that sentence, and that's a literal sentence from the novel Harry Potter. If it's exact match, that could be verbatim memorization up to some number of tokens L, and that could be one standard we adopt. But of course, it could also be relevant to think about something more approximate like edit distance. And in the realm of copyright law, if you produce something like this, you might already be in hot water, even though it's not verbatim memorized. And once we have started to travel down this continuum, you might also think, let's start to use the log probs themselves as a kind of rough metric for the degree to which something was memorized. And now you've brought all these things together, and I hope you're thinking of memorization as a pretty expansive, pervasive notion for language models, not purely verbatim, but actually existing on a continuum. All right, so that was the second preliminary. We gathered some more evidence, and then we have this heuristic to continue our journey. Results for verbatim memorization represent an extreme of a phenomenon that is pervasive in how LMs process text. And again, the reason we need this premise is because so much of the evidence that it's going to come later is about discrete memorization notions. And you need to somehow see past that to the log probs. Great. So this is the most important part, these memorization profiles. Please feel free to ask questions about the details of these things, because I really am trying to get you to the point where you see the tests. This is the first instance of a memorization profile that I know of. Tirumala et al. 2022. Let me orient you a bit around this plot here. We're talking about GPT-2 style models that are relatively small by today's standards, 125 million parameters, and the amount of text they're trained on is almost the same as the parameter count, which is very different from how models are trained in 2026. So it's a bit of an unusual scenario, but I think we can still take it on as a bunch of interesting clues. On the y-axis here, we have a verbatim memorization notion. This is going to be a discrete notion. It's the number of continuations of examples in training that were continued exactly. The blue line there is the training examples. And you can see this is a reminder about how unusual this is. We're going through many epochs of training. And so as a result, this model eventually memorizes the entire training set, which would be unusual for a more modern language model. But the really key lines here are these three colored lines. Okay, so what the authors did is in 3 independent training runs for this model, they injected a special batch of validation examples. They're just IID on the rest of the training examples, but they're a special batch unseen in the rest of the training examples. They did that at epochs 14, 39, and 63, and you can see that here. They have these peak memorization points where instantly the model memorized to some degree that batch. And then what happens is the memorization falls off and sort of ends up going toward the mean in a very regular way. Right? So they're kind of 3 very similar looking curves. Now, for Tirumala et al., they said, hey, there's no difference between the injection point. Because when they looked at this, they saw basically 3 identical curves. But with the benefit of hindsight, I think we can see that there is actually a downward trend here. Even at the resolution of this plot, you can see that this is higher than this one. So earlier checkpoints are able to memorize more instantaneously than later ones. And I would even venture that we see a regularity here too. The orange line is nicely nestled under the green line, which is nicely nestled under the red line. It's an effect that eventually disappears, but as you'll see in a moment, the combination of these 2 things basically is the memorization profile. And in subsequent papers and models, this is going to come out very strongly. We got this nice glimpse in this early paper. Now, a digression on the journey. This is going to turn out to be a dead end, but it's meaningful. In the Pythia paper, they actually did a bunch of experiments on memorization rates, and they report something that's kind of discouraging for the journey that we're on, because they say in their experiments, memorized sequences are not spaced more densely toward the beginning or end of training, and between each checkpoint, roughly the same number of memorized sequences can be found. So that sounds to me like we're not going to find an effect relating memorization to the training checkpoint. Whereas we just saw a glimpse of that with the Tirumala et al. Paper. Now, one experimental detail that's important here is that their measure of memorization is one of those discrete notions, and it's in fact a very strict notion because they are looking for exact continuations of 32 tokens following a 32 token prefix. And I think the result of this is simply that there was no chance to see the memorization profile. And in fact, there might be a second problem here, which is if you're that demanding about the memorization standards, those have to be strings that were seen a lot during training because single shot memorization is almost unattested. And as a result, they got spread out over the batches. And so the only time we were going to pass the threshold for their metric is with strings that we'd seen at various points in training. And that's exactly what would erode the memorization profile. And this is meaningful just because I understand that one member of RJS, the lead author team, was discouraged by this initially and then felt better seeing subsequent papers. This is maybe the most important paper on this journey. And I do just want to say this Lesky et al. Paper is a very beautiful and creative and deep paper, not just in memorization, but just as an example of very interesting and creative scholarship. So I highly recommend it. And this is, in fact, the paper where we very clearly see memorization profiles. Okay, so we're talking about a more modern model, Pythia 6.9b. And this is important in some sense. We're looking at every 1,000 steps checkpoints at every 1,000 steps in training, which is not very fine-grained, but it's pretty. We have a non-discrete measure of memorization, which is great. We're looking at differences of log probs, and I can talk with later on about how that difference is calculated. That's a very interesting aspect of the paper, but for us, it's just important that we are thinking about differences in log probs between a model that saw the relevant example and an approximate counterfactual that didn't. The top of the plot is the most important thing here. So we have, again, the checkpoints and the treatment steps for the different memorization tests that we're going to run. And the diagonal then is the instantaneous memorization of all of these checkpoints. And the observation here is that it's strongest early and kind of fades with later checkpoints. Might be hard to make out, but you can see the dots are darker on the diagonal here, indicating more memorization. And remember, I showed you that. That was the Tirumala et al. Thing where those three curved lines were kind of trending down. Earlier checkpoints being better at memorization than later ones. And then maybe more interesting is what they call persistent memorization. That's all these off diagonal things. And there's a very clear trend, right? So later checkpoints memorize much more than earlier ones. And the memorization kind of falls off in a gradual way, just like those curves from the Tirumala et al. It's a bit obscured here because although we have a continuous notion of memorization, they did a bunch of filtering for statistical significance. And so these dots appear to just end. But in fact, very likely that they kind of would just fade away if we let them. And that would make them look very much like those curves. And it's the same thing down here. So what they've done is zoom in on this particular combination of treatment step and checkpoint. And you can see like no memorization, exposure to the relevant strings, memorization rate goes instantly way up at this granularity. And then it kind of drops down quickly to something that's above the baseline, but much lower. And that's happening in this very regular way across all of these checkpoints, creating the memorization profiles. Here's another one. This is Chang et al. 2024. There's a lot going in this plot here, but we can zoom in on the most important thing. We're talking about OMO continued pre-training. The y-axis here is a probe for memorization. And what that means is that they have factual knowledge now. So it's not strictly memorization, but rather factual knowledge they're approximating as strings. But the criterion here is whether or not you generate the correct next token. So it's just like the other metrics we were talking about. The important line here, setting aside all this other annotation, is the blue line, because even though they're tracking this probe quality, they did put the log probs, which is the quantity that we're going to find most informative. That's the blue line. And so you can see they expose the model for the first time to the factual knowledge right here. And then after some time, we reach peak memorization, which is also peak log probs and peak according to their probe. And then after that, it starts to drop off, just like we just saw for the Lesky et al. Thing.
Is the window like all the steps in which that factual knowledge is in determined?
Oh, well, so they expose it once and then they're just studying the downstream effects. So it's kind of like, oh, is there, but just one exposure. Yeah. Yeah. We have this delay. And that is certainly due to the fact that the optimizer they were using, which they point out has a momentum term. And what that means is that initially when you experience this string, you're only getting a fraction of the impact of that example. And then the momentum term is a kind of moving average. So it accumulates the impact of that string, reaching a peak of around after about 30 batches. And then the momentum term starts to move on from this moving average and it goes down. So you get a delay here in this. It's important, we didn't see that with Lesky et al., but that's why I was emphasizing that they have checkpoints only at every 1,000, and that is not fine-grained enough for us to see the delay of the momentum term. But I have full faith that if it was more granular, the memorization profile would look like this. It's kind of like, there it is up there, and we've zoomed way in on a very narrow slice of Lesky et al.'s plot. And we're seeing that delay, but it's exactly the same shape here, just tracked in terms of log probs. Yes.
It seems like on previous graphs, kind of the rate of remembrance was dropping much lower, and here it's kind of remaining constant for a while. So Even though it is dropping.
It's a good point. Yeah, you're just to repeat it for the people on Zoom. Yeah, you're observing that it doesn't drop down as sharply as we saw. Even you could probably make it out here for the Lesky et al. I don't know why that is. It could be that we're looking at a very narrow window, and if we played it out over a much longer period, it would drop down. It does look kind of noisy here. Hard to say. Yeah, but this is kind of a reminder that we're piecing together a lot of very partial evidence into a full picture. I have just a couple more. This is great. This is from the paper that Jing Wang, my student, led, Wang et al. 2024. And this one is sort of puzzling for me in a deep way. That's often the story with Jing. She has puzzled me in a deep way. She's the J of RJS. Okay, so this plot here is measuring single shot memorization, because what we wanted to do in the paper is just show that that happens only in very rarefied situations. And it doesn't happen for realistic language model training. So we're looking at Pythia continued pre-training. We've got the steps along the x-axis, and it's very fine grained. And then we have verbatim memorization length along the y-axis. So we adopted a discrete notion of memorization, a very strict one. Single shot, as I said. And the whole point of this plot was to say, we don't really see much single shot memorization. You do see it at a kind of non-negligible rate for very small batch sizes, but not for larger ones. And that's what's unrealistic, is that no one would train a frontier model now with batch size of 8. And so if you train a big model, single shot memorization is simply not going to happen. That's all I saw in this plot, is blue above green above orange. But what Jing saw is much deeper. So she saw that peak delay that comes from the momentum term because she had been a student of that Chang et al. Paper. So she knew that was coming. And when it's pointed out to me, I do see that you see these kind of offset peaks at different points here, depending on the batch size. And that's coming from the momentum term. And then the biggest puzzler is, to me, I didn't really see any downward trends. But for Jing, it looked like these lines were trending downward. And that would be the memorization profile, right? In this discrete space here, you went up and then you went down like this. And so I said to Jing, hey, maybe they look down to you, but to me, they kind of look just like noisy. And she was like, oh, Chris, come on. If I used something like log probs on the y-axis, they would go way down. And I think she said that because she has lots of experience with this and had, in fact, explored lots of non-discrete notions of memorization in earlier work. So she had very deep intuitions about this. But I was like, well, I'm not sure I should just take that for granted, Jing. So sometime later, she sent me this plot, which is just exactly the plot we were just looking at. It's a different model because I think she prefers OMO to Pythia now for this memorization stuff. But it's exactly the same protocol, single shot memorization, except now the y-axis is the model loss, which is the negative of the log probability. So this is going to look upside down. That's another adjustment we have to make. But obviously here you can see we have a rapid drop in the loss, which is a rapid increase in the log probs. It reaches this low point about 30 steps after exposure, just like in Chang et al. And then it kind of goes back up, regressing sort of toward the mean. So that's just another memorization profile, in this case for single shot memorization. And this was like the missing link for me. And now I saw why RJS were inspired by Jing's paper to start to put all these pieces together. And so here's just another reminder, like that's the Chang et al. Plot. And if you just turn it upside down, then it looks exactly like this one, right? Down and then up, down and then up, just like Lesky. And if you squint really hard, just like that Tirumala et al. From that earlier paper. Okay, so we have gone a long way. We gathered all of this evidence here and arrived at this heuristic. A model's log probs for a sequence it is trained on will peak soon after the relevant training step, the exposure point, and then decay predictably over subsequent steps. The heuristic. We are about to see the palimpsest. Before I do that, any questions? Anything I can clarify about that bit of evidence I showed you?
In the causal, like in the longer steps of window, we see like in the unit of k, we didn't see that gradual Yeah,
Here.
this one.
Right.
Gradual increase of memorization. We have an insight.
You're talking about this narrow slice here. We just saw it leap up.
No, like it's a sudden drop, and but then over from 70K to 130K, we didn't see like a clear increase. But if it should be if it's consistent with students' paper, then we might see the memorization.
Right, I see what you're saying. So what you'd expect based on what I just said is like baseline, up, down, and then it kind of up like this. And that's interesting. We don't see that.
No, isn't it good? It's flipped
Um,
because the drop is now positive.
oh yeah, wait, right, that's the issue, right? We're so narrow here that what we'd actually expect if we had more fine-grained notion here is there'd be exposure and then sometime later peak and then drop down to more like this. So I think just too much of the Chang et al. Curve is hidden right now for us to see the dynamic you're talking about. That was a puzzler for me too. I'll confess to you that I wrote to Jing and I was like, why don't we see the delay in these Lesky et al. Plots? And she was like, just look at the y-axis. She was much nicer about that, but you know, that I was like, oh yeah, it's only every 1,000. And we're talking about an offset of about 20 steps. Other questions? Yes.
So then like the optimizers and the radians and all of that, they essentially act as just like a moving average over the data points.
That's a good description at a high level of what the momentum term for those optimizers is doing. Yeah, and so if you do these plots with an optimizer with no momentum term, they don't have this, I believe. I think they just kind of smoothly go into the. Oh, sorry, they don't. Yeah, that's right. I keep getting myself confused. They don't have the delay, which we see in all these different places.
Yeah, so if we didn't have the momentum term, or what, if we didn't have this delay at the peak, it would essentially just be similar to like what you would expect like a moving average to be, where it's, I mean, the data point is not included, and then all of a sudden it's like the most important, and then
Yeah, it would look like the Lesky et al. Ones,
Yeah.
where it just jumps up and then drops down. Yeah. Which is obviously interesting. I have a citation for this later. Studying the role of the optimizer in creating these memorization profiles could be really interesting. And it could be that if you know about the properties of the optimizer, you have a more powerful test because of the extra information that gets conveyed. Yeah. Okay. So these are the first plots that the RJS team shared with us, as far as I know. They look like this. So 6.9 BD duped. We're looking at different checkpoints, nice and fine grained. And then up here, I have samples of training examples from exactly that sequence, exactly that training order. So like checkpoint 5, 25, 50, 75, and 100. And it's really important that these are aligned because we're studying the relationship between the loss here, which is the negative of the log probs, and this ordering here. Okay. And so, for example, let's imagine that we zoom in on about checkpoint 30 there, this black line, and you look at the log probs for those different training example bunches. This is the average log probs. You see that 25 is by far the lowest, followed by 5, and then the rest of them are kind of just clumped up there. The ones from the future are just sitting on the average of this whole line. But it goes 25, 5, future at checkpoint 30. Let's do another one here. At about checkpoint 55 or so. This is 50, then 25, then 5, and then the 2 from the future. So once again, I can read off the training data order from the log probs. Here's another detail. This is at 80, and I just labeled them 5, 25, 50, 75, with the 100 one, the one that's still in the future. And so again, I have a perfect correlation between the log probs and the training data order for these examples. And that just is the palimpsest. And it's fine-grained, but it's actually fully organized down here. If you do this with Pythia 6.9b not deduped. So this is a very similar model, but just trained on a different order of data. But your batches come from the deduped one. There are absolutely no trends like that. All of them just sit on the same line. And that probably is what you all need to see that there is a statistical test lurking here. Because I could just set up the null hypothesis of independence. And if I fail that independence test, probably I'm talking about the same model. Just one more note here. If you want to increase the statistical power of this, you can do that by incorporating the fact that individual examples will have different log probs. And you effectively do that at the example level by taking these two and subtracting them out. And when you do that, you get very dramatic instances of the palimpsest. Now it is just obvious how nicely organized these are. You always get a regression to the mean, but you preserve the order. And you can see at the end here now the order is perfectly correlated with the checkpoint. And that's it. So we made it. We traveled all the way from our campus through all of these papers scattered all over the place to the palimpsestic tests. How am I doing on time? I have a few minutes just to show you a sample of results from the paper. But before I do that, any questions, anything I can clarify? I'm hoping the test I showed you at the start feels much less obscure and random now.
Do you need a charger? I'm just seeing.
Oh yeah, it's not charging. Should we just see what happens? I think I think it'll be okay. For the test, right? So here's what I've been describing is what we in the paper called the query setting. Oh, Lisa, are you right? I'm really about to.
I'm anxious.
I don't want people distracted. I think I thought it would charge through this, but it's not. Let's not worry too much. We'll see what happens. Right, so training data, this is what I just showed you. Training data order, assigned log probs. We're testing the correlation. We do that in terms of ranks, and the null hypothesis is that these two are independent quantities. You might wonder about how you're going to set this up as a proper hypothesis testing framework. We have a bunch of guidance for you in the paper about how to do that for different scenarios. So for example, here I've got number of sample tokens. This is the amount of the training data order that I'm going to use to run the test, because I don't need to use the full sequence. And here I have different p-values. Now, clearly, if you can sample more tokens, you'll have more power for your test, because these p-values kind of like go down monotonically with more evidence. And you might think like, if I can afford to do 10 million tokens there, then I could set the threshold at like p at 0.0001, and I would have properly calibrated the test in the sense that I'm not going to unfairly reject the null hypothesis, and I'll have high power to detect like true positives for this case, because all of these things are kind of organized down below here. But if you have a different budget, then you could set this differently. And you can see also from this plot that you get much more statistical power if you bring in that reference model that I mentioned to subtract out the general variability in log likelihoods. Here's an interesting little bit of sleuthing. This is the case of Pythia 2.8b deduped. Lesky et al., in an appendix to their paper, they just note we excluded the 2.8b model from the results since we found a potential mismatch between the available checkpoints and the data order used during training. They decided it was so suspect that they left it out. When we run our tests, the p-values tell a very dramatic story. You can now see directly that that model, which is called the deduped model, was actually trained on the non-deduped data. You see that as this outlier p-value here. And we said that in our paper, and then I am pretty sure I can say that Stella Biederman from Luther confirmed that we in fact, that she had in fact messed up, and like when they reloaded a model or something, they reloaded the wrong data, and that created this anomalous data point. And I think Stella is going to fix that. That's a nice case where our test did something useful. And this is a kind of representative example of the results that we get for derivative models. This is like when I've fine-tuned post-training a base model here. So I've got OMO, 3 different OMO models. And then you have all these derivative artifacts of different of the OMO things. And you can see from the p-values in log space here that you get really low p-values for the models that are derived in this corresponding way. So nice evidence that we can, in fact, with high accuracy, detect what the underlying model was. One more thing, this is the observational setting, which I'll mention just quickly. Let's imagine we're in a scenario where we don't have direct access to M2. As I said before, we just have training samples from it. Let's call that this text down here. We can still run the test. And the way that we do that is we take the training data order for our model M1, and we create a bunch of, could be like n-gram language models, simple models on contiguous parts of that training sequence. And then we just operate in the space of those n-gram language models. So we look at the scores assigned by them to that text that we got from the model service. And again, if we see a correlation now at the level of these models in their ordering with the probabilities assigned by those models, we've got a version of the test. Now, it's a much more demanding test, right? We have very limited access to this model. And here's a bit of evidence to kind of help you calibrate. What we're doing for these examples is looking at the first 100,000 training steps from a Pythia model. So you could think of that as like an approximate view. We've got 100,000 n-gram models, one from each step. That's an approximate view of Pythia 6.9b deduped at that 100K setting. So here I've got different steps, and you can think of this as the original model, and these will be our ability to detect fine-tuning because those are continued pre-trained versions of this 100K step. Looks like M1 and M2 are the same, and these are all derivatives. This is the length of the text that we need, and you can see they're quite long, from 640,000 tokens all the way up to about 20 million. For detecting the exact same model, we get low p-values starting at around 1.28 million tokens. So that looks pretty good. But as we get to these derivatives, we really need a lot of text to have statistical power here. And this just comes from the fact that we have such little access to the underlying model. But there probably is an opportunity here to increase the power of this test in this kind of setting. Right, so this does mean that the best application, if you have to run this test, would be like really large scale social media monitoring, where you could get massive token counts and really start to detect what was happening in an entire ecosystem. Whereas the previous test will work even if it's just like one model that you've got access to. Let me wrap up then. I wanted to look ahead a little bit. This is the adventure that we just went on from our campus to the tests. But it's just a small part of the journey that we could be on. There's a whole big map here. And in particular, let me map out a few other adventures that you could join us on or travel yourselves. First, we could think about the role of different sampling strategies. We've been thinking about greedy decoding. The sampling strategy does matter, especially for the observational setting for our tests. Could be a factor. We could leverage it to our advantage. We could also think about why language models memorize at all. And this is a provocative paper saying that diffusion models don't memorize, or at least not in the same way that regular language models do, which could give us a glimpse at the underlying mechanisms behind these memorization profiles, which would be illuminating in its own right and also give us power to think of different tests. And you could also worry about whether people can hide from our tests. That would be an important part about operating in this ecosystem, is that we also imagine what it would be like to be trying to foil someone who was running the palimpsestic tests. And this is a very interesting paper that is not about that, but it is about how memorization might have global impacts on the learned parameters. And they do have some techniques they can use to kind of erase parts of the memorization by doing global operations on the weights. That could mean that they can kind of hide from our tests. I haven't explored that idea, but it's something to think about. So let me wrap up here. I just want to thank Rohit and Sally and my senior authors, of course, and especially Jing for helping me so much with this talk and the blog post, and in general, just talking about all of these ideas with me so much. She has a very deep perspective on them, and that has really helped me in understanding how RJS as a group managed to come up with these tests. So I'll wrap up here. Thank you very much for all your comments and stuff. It's been great. Yeah.
That's a question. I'm wondering, I think it's interesting in a reverse way, but can we train a model to achieve a higher score at the palimpsestic test? Like to trick people that this model is a derivative of M1. For example, can we use distillation from M1 or maybe using contrastive loss to trying to map M2 like closer to.
This is a great question. Yeah, so we haven't explored the particular strategies that you just defined for trying to hide from the test. But one thing we do in the paper is explore lots of different regimes of continued pre-training. So suppose that you created M1 and I stole it from you and I want to hide that. One thing I might think I could do is just start taking different orders of the training data, which maybe you released, put them in different orders and continue pre-train the model, right? In the hope that that will wipe out the original ordering, but it doesn't. In fact, many epochs of training remain embedded in a way that's detectable from the palimpsestic tests. And if you want to hide, really hide from the test in that way, you have to do so much more continued pre-training that your original model theft was pointless, because you basically have to retrain the entire model. So that feels pretty good to me, but that does not address the more clever things that you just described. And it could be that those provide ways for me to hide from you in these settings.
Yeah, so you mentioned at the beginning that this was robust to like only if you had a subset of the training data, or if the model was like souped or something like that with another, or also but and so are all these things just things that undermine the statistical power but can be overcome if you just have a significant amount of data or something like that?
They don't necessarily undermine it. So just as a representative thing, like let's see, I had them here for the query setting. These are all derivative artifacts. So not for nefarious purposes. People were just taking OMO and improving it, and they did various things to it. And as you can see, we really get very low p-values even in those cases. And the question is, though, if I decide to do this kind of manipulation specifically to hide from the test, I think you end up back at this answer that you have to do so much work that your original model theft was kind of pointless.
Okay.
But that's just what we see in continued pre-training. That doesn't mean that there isn't some regime that would support what you're after.
And then I guess the second question is, you said that even without having access to the like M2's log probabilities, just based off of what it's generating. What about if M2 wasn't trained with M1 weights, but was trained off of like M1 generated data?
Oh, yes. Okay, this is another great question. So basically you're asking, can I catch? So in the scenario where I created my model M2, you've got your M1, but my M2 comes from some other thing. But what I am doing is taking your model and distilling from it.
Yeah.
Right. And so this is a very important case where, like, did this startup create its model by just stealing a bunch of data from Anthropic? Right. That scenario. Yeah. They did try experiments on that. And that's a case where you have to have distilled so much that I think the size of distillation needs to be as big as the size of the original model. So if it was distilling from, for it to be detected.
Yeah.
So if you distill from Claude, it needs to be that the number of examples used to train Claude.
Yeah.
Which again is not very practical, but that sounds like an opportunity to me.
Right.
And I just want to emphasize that of all the scenarios you could imagine, especially if you're on the side of these big tech companies, that's the most important one because they're very worried about this kind of distillation. So you could help them out by having a good test. Yeah.
Yes,
I have a follow-up. Sorry, go ahead.
Could contribute to a revival of a new version of curriculum learning for LLMs, in the sense that, okay, if there's this profile of memorization, that may be very different from how humans work. So the old idea of curriculum learning may still be void, but maybe there is therefore a strategy that could make training more efficient because of these ordering effects actually having such lasting impact on what models do.
Oh yeah.
Do you think that could be interesting?
Absolutely. I mean, and I guess we can already infer from all this evidence that if you want your model to memorize some examples, you should put them late in the training. And if you're really worried about that, you should put them early. So that's probably just a glimpse of the opportunities that you're seeing around what you want the final state of the model to be and how that pertains to the training data order. Yeah. Yeah.
I also have a related question. It's not a direct thing of your study, but I'm thinking, do you think there will be a threshold where you can cut so that above that threshold, it means it ever appeared in training data somewhere, and then below that threshold, the probability threshold means it never appeared in the training data.
For a specific example?
Yes.
No.
Okay.
Yeah, because of those memorization illusions, for example. And that really is just the full problem of membership inference, right?
Right, exactly.
Yeah, and so the answer is no, and I think the memorization illusion shows why, because there could be something that is in the training data, but the causal factor that causes the model to produce it verbatim is not its occurrence in the training data, but rather a whole host of other factors.
Okay, so it's more like the reverse doesn't work. It's more like this,
Think
right?
that's
It
right.
appeared and then it will show a trajectory, but then it's not like when it didn't appear, it will necessarily have low probability.
Yeah, maybe the problem does go in both directions. It could have very low log probs. And so like every test you'd run would say that was memorized, but it wasn't in the training data. It was just a kind of reconstruction of other things that were in the training data. The reverse is also, of course, possible, which is that it's in your training data and your model appears not to have memorized it. And in fact, single shot memorization is so rarefied that that's going to happen a lot, in fact. If you put all of those things together, you could have a single example in your training data. Your model could produce it verbatim, but the causal factor isn't that it occurred in the training data, but rather everything else that was in the training data.
Right, but because you produce this trajectory of when these data appeared in the training, you will see a probabilistic trajectory, right? So it seems to me if this data have ever appeared in your training data, then it's inevitably that the probability will be low. Otherwise, like there must be some memorization still maintained in the model such that this whole test will work, right?
Yes. Yes, I see what you mean. Yeah, I think maybe there is something there. I'll just say at the individual example level, things look like this. So, and really like this is the null hypothesis here. That there are views on this data that would provide much better fidelity.
There was a question on this.
Yeah.
You
Well,
can
then you can-
ask.
You can just read it.
Yeah, you can unmute yourself
Yeah.
also.
Oh, can I go ahead?
Yes, we can hear
Oh,
you.
this is still gonna work. This is great. Yes.
Yeah, so the question is, to what extent you think this method will have false positive in flagging something as derivative, but it's not? Or is it because it's correlation test, so it just give us like a degree of the chance it's a derivative? And another follow-up question to that is, can we distinguish the behavior of memorization versus the intent? Because I mean, I was just thinking like a game people like to play improv, like called convergence. People say like 1, 2, 3, they spill the word, and they keep spilling words that can run. In the end, they will converge in the word they say together. So that behavior itself looks very similar like a memorization, but you wouldn't flag that behavior as memorization. So I just wonder if there's any chance that the model behave like they're memorizing, but the intent is not.
Right. For the first question, the one about the false positive rate, I guess the idea is that you ideally are in a setting in which you have lots of text you can use. So the compute resources to use many examples, and that increases your statistical power to the point where you can put the p-value very low. And it does look like, I mean, they can get fantastically low. So you could be very, very strict about the context in which you reject the null. For the second thing, I think that is kind of in the neighborhood of the memorization illusions, right? Where for all the world, it looks like a string was verbatim memorized, when in fact it's a consequence of a much more complicated process in the language model. And yeah, I think we should embrace that. It certainly has consequences for simple stories around how we're going to catch people doing copyright violations and stuff like that. But I think it also represents something pretty deep about how these models might be storing strings that they need to appear to have memorized, and also the underlying mechanisms behind memorization.
So I guess the inference we're drawing is more based off the behavior of memorization. Like that's how I want to label it as.
Right, but I
memorization.
will say that, so I didn't get to talk about this, but the Wang et al. 2024 paper is in fact a lot about the underlying mechanisms, and we do a lot of intervention-based experiments to try to figure out which representations in the model are participating in the memorization behavior. That's actually what the memorization, that paper is about. We just incidentally saw all these memorization profiles.
Okay, sounds good. Thank you.
Yeah, thanks.
Follow up on that question, actually the false positive question struck me. Is it possible, because it feels to me, for now you showed a lot of like, if it is derivative, your method will be decoded, right? But what if it's two company, but they happen to use the same data in the same order to train our model, right? Their architecture and all that can be different, but it seems to me the probabilistic signature will be the same.
Yes.
Then in your test, it seems to me it will be positive as well, even if it's not. Basically, if they actually separately train their model, but for example, if they take the web down and then they didn't shuffle and they take the same order, then it seems to me it's possible that this will give false positive.
It will. I'm sure it would in that case. Yeah, and an assumption I could mention here is that, to be precise, the assumption is that there are n permutations of the training data examples. So the chance that two people chose the same one is like 1 over n. And that, n there is like astronomical. It's too small to describe the size of n. But if, of course, the world intervened and they just happened to use the same training data order, all of that is out the window. Yeah.
How long is each training example that you're computing the log probability over?
So how long are they for these models?
Yeah,
And somebody who trains these models would know. I think they try to pack them all very densely, right? So they're all some regular length.
because that is basically the saving grace for that method, right? So that's how any individual frequency of words or grammaticality would just wash out, and therefore the memorization profile can live because these are long enough, right? So that's what was something I was wondering about.
I see what you mean. So if you did reduce them all down to single tokens, there would be just an opportunity for variation that would allow us to detect.
Exactly. Yeah.
Yes, interesting. That's as far as I know, that hasn't been explored, the effect of the example sequence length. Mostly that hasn't been under our control because we're taking like Pythian models or OMA models. Working with them.
What about the example location? Like, is the later ones in the training better at distinguishing than the earlier ones?
I think yes, in the sense that the later examples will be memorized better than the earlier ones.
Yeah, it looked
They were
like from the
converging
graph, right?
together,
They were
like-
converging.
Yeah.
What is converging in that? What
Like
quantity?
the log probability of the samples in different steps were converging together. So I'm saying that the very early ones maybe converge so much together that you can distinguish anymore based on those. But if you use those samples that you're choosing to evaluate on from the later in the training, maybe they can be a better distinguisher for this.
It's a great question. And I feel like we do have experiments that speak to this. Maybe you can check out the paper, because an interesting thing about Pythia is that they underwent 2 epochs of training. And so from our perspective, that kind of creates 2 models. And you can think about using one to detect the other, and also different points inside the sequences. And I think some of that does matter. Yeah. And there's a very strong result that you get the strongest signature by looking at sequences that are early in the examples. So prefixes of examples are memorized better than sentences. Yes.
I'm just wondering, go over it and think because you perhaps students at that time, your intelligence from class that's maybe that was the.
Oh, I see. So specifically, you're asking if I have a very particular conditioning environment, whether the effects on the token generations that come after
Yes,
would be eroded.
right, no, or absolutely not be, but. Programs, so.
And this would particularly impact the observational setting where I'm just using texts that are out there on the web. It's a great question. I don't know the answer. Yes.
Yeah, I guess, so if you had, say, a limited amount of data. Because, you know, you're showing that more data, obviously more statistical power, but if you, for whatever reason, had a limited amount of, I don't know, compute or something like that, it would be best to take like equally spaced out from the entire training data, because then the like n log prob would be
Ah,
more spaced out, or what you
that
like.
might be right. Yeah, and then you would look at prefixes of the examples. I think this is guidance from the appendices of the paper. Yeah.
Okay.
And this would help you with limited resources. Yeah, and for the observational setting. Now, in fact, what they do, I describe them as n-gram language models, but what they actually do that proved very effective is just look at n-gram overlap. So very simple notion of language modeling, and those counts properly transformed create the scores that support the test. And that suggests that if you have some ideas about which strings to look at, then you could maybe very efficiently gain high power.
Yeah, I have a question that was along those lines, where I was wondering, we were talking before about doing this with just a sample, so that was a random sample, because if it wasn't a deduped model, then perhaps there's cases where if you're looking at high frequency events, you might impact this.
Specifically for the observational setting? Or right, like, so you're just like in the limit case where the only messages we can find from M2 are just kind of like template text that every language model produces, like, thank you very much. We're not going to have any power to create good n-gram language models to support the test. Yes, so that's right. So there is an assumption about diversity in there, that we've got texts that are kind of like IID over something like the training distribution to support the test, which cuts both ways, right? So we can, if we're using M2 in this nefarious way, we could make sure we generate texts that aren't detectable. Conversely, if we want to increase the power of our test and we can produce text from M2, we could do it strategically. Yeah. Like find texts that are really representative or interesting of our training data.
Yeah.
And use those. Yes, yes.
I think we're running out of time for our talk. So let's all thank our speaker again.
Thank you very much. I'm sorry to the people on Zoom that my computer died. Thank you for saying.
Meeting